Hi, this is Dr. Andrew Chrysler teaching electromagnetics. In this video, I'm going to show you two approaches for understanding the displacement current term in Ampere's equation. So the displacement current term is here. This is the Ampere's equation as we saw it in electrostatics. And I'm going to show you two approaches. One comes from the Ulaby textbook. The other comes from textbooks such as these two. So the Ampere's law in the electrostatic case has no time-varying term. However, the time-varying form that exists looks like this, and it does include this partial derivative of the electric flux density. And we're going to see why that term exists via two approaches. The first approach is going to start with this as this form of the Ampere's equation, the time-varying form. We're going to start with this form being the known implicit solution, and we're going to see why it must exist. So this is the first approach. To start with this approach, we look at this term, and we recall that if we were to take a surface integral, so if we're going to add up all of the current going through this surface, we would call that a conduction current, which is equal to all the moving charges that go through some ds that you've chosen. So starting from Ampere's law, we know that we can get that conduction current. We know that if we take that surface integral, we'll get that conduction current. So we'll take surface integrals for both sides. And when we do that, we can see that this term, right, is going to be equal to a conduction current that describes a bunch of moving charges. So we can rewrite it like this, and we still have two terms that are these surface integrals. Now, moving forward, we notice that this form, we could apply Stokes Theorem to this, and we could change this from this curl into a circuital loop integral. And this should look pretty familiar, as this is something that you likely did for the Amperian loop integrals in the magnetostatics case. So when we do that, we can see that this circuital loop, we can transform this left-hand side into the circuital loop integral is equal to a conduction current, and these are moving charges plus this time-varying term. And we still don't know exactly what this time-varying term means, but let's see why it must exist. So that time-varying term, we'll define it as a displacement current, and that's due to the way that the electric flux density changes. So therefore, that circuital loop integral, if we assume this time-varying form, must be equal to a conduction current, which is moving charges, plus a displacement current, which comes from a changing electric field. Now, in the electrostatics case, we knew that this rate was going to go equal to 0, and therefore the displacement current is equal to 0, and this circuital loop integral is equal to just the conduction current. And this is how we solved many problems in our magnetostatics case. So why must there be that second term, that displacement current term? Well, let's take a look at a circuit. The circuit is powered by a time-varying source. In the first part, we have a wire, and the current in the wire is a highly conductive wire. Therefore, the E field is equal to 0. I'll link a video to the boundary conditions. But that is something that we know must be true, that we've built up previously. Therefore, in the first part, this current 1, the displacement current must be equal to 0. So the ID 1 is equal to 0. But in the second part of this circuit, it goes through a capacitor, and inside of the capacitor we have the perfect case where the conductivity inside of the capacitor is equal to 0. That means that no charges can actually move through this. So in the perfect case, there's no moving charges inside of that capacitor, therefore the conduction current must be equal to 0. Therefore, in order to rectify this case where we have a current going into a capacitor and going through it, we can see that there must be two different types of current, and they must be equal to each other. Therefore, we need to have both these terms included in our time-varying Ampere's law, one to account for the actual moving charges and one to account for the changes in the electric field due to a voltage source that changes with time. So the approach 1 starts with both terms. And this second approach will begin with the electrostatics case, and we'll see why we need a displacement current. So we start with the electrostatics case, and we recall a vector identity. So this is something that you should already know, but basically the divergence of the curl of any field is equal to 0. This is just something that we know. Curls have a divergence of 0. So starting from that, if we take the divergence of the left-hand side, we know that for the H field, that would be equal to 0. So by definition, we have the divergence of the curl of H is equal to 0. Now, that must mean that the right-hand side, if we take the divergence of the right-hand side, is also equal to 0. However, J is the motion of charges, and we know that that charge density would be rho v. So the divergence of J is equal to the negative partial derivative rho v dt. And this is sometimes called the continuity equation, but this is something that we've also previously defined in our electrostatics case, or in previous parts of this text. So this means that if we have the left-hand side and the right-hand side, the implication is that this would only be equal for, or valid for, static conditions, because this divergence of J is only going to be true when it's only going to be equal to 0 when this dt term is equal to 0. So if it's only equal for static conditions, we need something to account for what happens under dynamic conditions. So we're going to propose a second term for this equation. We're just going to use a placeholder g. So we'll propose a dynamic equation, which is Ampere's equation plus another term g. And we'll see that what this g term is, and we'll see that it's the same as what we got in approach 1. So let's take the divergence of both sides now with our new placeholder g. And we still have the divergence of J defined as the partial derivative of the charge density. But that must mean, because this is equal to 0, that must mean that the divergence of G must be positive, the positive partial derivative with respect to time. So we can rewrite it like this, where we have our new placeholder idea of G as is being equal to these two partial derivatives. So we have two things that add up to equal 0 under this case where we are taking the divergence of both sides. Now, when we recall that Gauss's law tells us that the divergence of the electric flux density is equal to the charge density, we can see that there is a charge density that appears here and here. So we can put this in, so we can see that this charge density is here. We'll place that in here. And now we have an equation where we have the divergence of all of our terms. And noticing that, we can remove the divergence from both sides, and that leaves us with this time-varying version of Ampere's law. And so that means that this G term was actually going to be related to the electric flux density. So these are two approaches for understanding the displacement current and why it must exist. It's a little bit tricky because this displacement current forces you to recall a lot of information about vector calculus and about the previous things we learned in magnetostatics and electrostatics in order to understand why this term, this partial derivative term, must be added in order to create a proper time-varying version of Ampere's law. Thank you, and I'll see you in the next video.